Iterators, relational operators, and joins. Recall from last lecture how we said that an SQL query is given to a query optimizer, which uses relational algebra internally to put together a logical query plan, which then it converts into an optimized physical query plan, every relational operator being associated with an implementation that can be run that we called an iterator. So today we're going to learn more about these iterators, and we're going to learn about some specific iterators for joins. Now, given a relational algebra expression, we can think of it as a query plan in which the edges encode a flow of tuples to the vertices, which are relational algebra operators. The source vertices at the bottom are table axis operators. Now, the way to think about this as a flow, recall that every input to a relational operator is a relation, and every output of a relational operator is a relation. And so it's tuples in and tuples out. And you can see the individual tuples from these relations flowing along these edges incrementally as we run the query. This is sometimes called a data flow graph. And data flow graphs are used not only in traditional relational database systems, they're widely used in distributed and big data systems, and they're used in other areas as well, like deep learning systems and even some hardware specifications. Our query executor in the database system is the module that runs the relational operators. The optimizer selects these operators to run, and then the executor is going to execute those operators. And each instance of the operators is going to implement an iterator interface, which is responsible for efficiently executing the operator logic, forwarding tuples to the next operator in a data flow fashion. So you think of this tree, and each one of those operator instances, each one of those relational operators implements that iterator interface. So for example, in this tree, we've got a number of different implementations of interfaces. We've got some scans at the bottom that are implemented using indexing. We've got some on-the-fly iterators for select and project, and then we've got some join algorithms implemented as iterators as well. And we'll look at all of these techniques very shortly. The iterator interface more generally looks like this. All relational operators are implemented as a subclass of a class iterator. It's got four methods: setup, init, next, and close. The setup method basically just constructs that data flow graph. It tells the iterator who its children are, and the iterator will remember its children as a list of inputs. And this is just for setting up the topology of the graph. The next three methods are the ones that define the implementation of the iterator, and they're specific to each operator that we're going to implement. Init, or initialize, is the thing that sets up any state that we're going to need while running the iterator. Next is a method that returns a single tuple from that iterator. And when you say next, you eventually iterate through all the tuples that will be produced by that operator, hence the name iterator. And then the close method closes the iterator. Note that this is a pull-based computation model. So if you have a client, like a console, it can call init on the root of one of these iterator trees, and it will recursively pass that call down to its children, and then return to the client. The client or console will then call next at the top of the tree to ask for a tuple. Now the root of the tree may not have a tuple ready, so it may have to call its children to get some tuples from them. And so recursively it will call the children requesting that they produce a next tuple. And then when the root is ready, it will return to the caller. And all that happens in a single thread of recursive function calls. Now the init and next implementations for different operators can result in either streaming, sometimes called on-the-fly behavior, or blocking, sometimes called batch behavior. By streaming behavior, I mean that for every call to next or call to init, a small constant amount of work is done. So think about next. If I say next and it only needs to do a small amount of work per tuple, then I have a sort of constant flow of data just by saying next, next, next. And I know each time it will only take a constant amount of time to return. By contrast, a blocking operator does not return from next. It does not produce any output until it consumes its entire input. So I might say next for the first time on the root of the tree, and it will in turn say next to its child over and over until it gets all the data from its child, all the rows from its child, does something to them, and then returns to me a first row of output. So that would be a blocking operator. And we'll look at examples of both streaming and blocking operators in this lecture. Now these iterators are encapsulated. These methods set up init, next, and close that they call amongst each other, they don't need to know what subclass of iterator, what relational operator that is being implemented below them. They just know that they're talking to an iterator. And this allows us to do what we said could be done with the relational algebra, which is to mix and match relational algebra operators in any way we like. Finally, note that iterators can have significant internal state that they don't share with other iterators. It's private to the implementation of the iterator. That state could be things like partitions for sorting or hashing. So they could be very big. They could be as big as database tables or even bigger. Or they could be small and simple state of the iterator's current computation while it's saying next. But iterators do have internal state, and we'll see how that's managed in some examples coming right up. So our first example is going to be select, which is a streaming or on-the-fly operator, and we saw it in our original query plan marked as on-the-fly select. So the init for select is going to be past the select predicate, and it's going to first call its child to initialize the child and any of the subtree logic that's below it. When the child returns from init, then the select operator will set up its local state. It's going to have a local variable called pred, which holds the predicate, and a local cursor, which is going to call current, which is going to set to null. Now, when you call next on a select operator, it works like this. While current does not equal EOF, end of file, or end of fun, if you like, and the predicate is false on the current tuple. While that's true, that means that we can't return this tuple because predicate is false, but there's more tuples to go. So we'll say current equals child.next. And so you can see we're asking the child for a new tuple. Okay, now we keep doing that until we either hit the end of file from the child or we find a tuple that satisfies the predicate. In either case, we're ready to return from our next call, and we'll tell whoever called us, here's the current tuple, which might actually be end of file for us as well. So an end of file on our child is passed back as an end of file for us. And then of course close, we don't really have anything interesting here to do, so we simply close our child and then we return. So that's a very simple iterator. It mostly just passes selected tuples through from its child to the output.